So, okay, let's get started. So last time we discussed FP representations of a certain special kind of group. What was special about that group? Well, it was an extension of a cyclic group by a cyclic group. So that you can say that it's a fairly simple kind of group. Cyclic groups are the simplest, but an extension of a cyclic group by a cyclic group should be sort of next simple. Now, it was not an arbitrary extension. The quotient is a cyclic group with a canonical generator. A generator is given to you. And the subgroup, the normal subgroup, right, is something which is of order prime to P. Actually, it was a subgroup of L star, where L is a finite extension of K, and K is a finite extension of Fp. So we have fixed prime number P, we have the field Fp, we have a finite extension K of Fp, and a finite extension L of K, and then you have L star, the multiplicative group, and you have a subgroup of this multiplicative group. That was the normal subgroup of the extension. And what is the action of the quotient on this kernel? What is the conjugation action? That is given by raising to the power Q, where Q is the number of elements in the finite field K. Okay, so we had that kind of a group G. G had a normal subgroup T, which had E elements, and which was a subgroup of L star, and the quotient was called sigma. G by T is sigma, and sigma has how many F elements? The order of sigma is F, and there's a generator which is little sigma. So let's just look at this particular case, which is mentioned here in number 24, where the group G is going to be turned out to be isomorphic to S3. We have earlier looked at cases where it was actually a cyclic group of order 3, or even maybe order 2. We didn't even mention it because it's perhaps the simplest possible thing, simplest non-trivial thing. So order 3 we have looked at. And now let's look at something which is not itself a cyclic group and which is not even commutative. So how do we come up with this example? So you take P equal to 2. And this Q, which is of course a power of P, is congruent to, Q is a power of 2, power of P, P is 2. And Q, let's take it to be congruent to -1 modulo 3. Okay, this is a special case. We are looking at some special case, and let's take F to be 2 and E to be 3. So the order of G is of course going to be 6, because the order of E is E times F. E is the order of the subgroup, the normal subgroup, and F is the order of the quotient. So the order of the group G is E times F, and since E is 3 and F is 2, the order of G is 6. Fine. And what do I say? So that sigma is equal to Z star. Well, I mean, any group of order 2, sigma is a group of order 2, so it's any group of order 2, you can think of it as being Z star. But more importantly, G is isomorphic to S3. Why is that? As we said, we must have mentioned, did we mention this? Now, I don't remember whether we put a hypothesis on G that it's a semi-direct product. Perhaps not. So let's look at the notation. But in this case, of course, obviously it's a semi-direct product because the quotient is of order 2 and the subgroup is of order 3. So it's a semi-direct product. And therefore, well, so it's either Z mod 6 or S3, right? But which one is it? That depends upon whether the action of this Z star on the kernel, which is a group of order, cyclic group of order 3, whether that action is trivial or it is not trivial. If it's trivial, then of course just the group G is just the product of this group of order 3 and Z star. And if it's not trivial, then it is isomorphic to S3. But because this Q is congruent to -1 modulo 3, and the action is raising to the power Q. So the action is, I mean, it's not trivial. On this group of order 3, it takes x to x inverse instead of taking x to itself. If Q had been congruent to 1 modulo 3, then it would have been the trivial action and the group would have been just a product of Z mod 3 and Z mod 2, which is of course also the same as Z mod 6. But here the action is not trivial, so we are getting S3, this semi-direct product, right? And L tilde is equal to L. So L tilde was obtained from L by adjoining a certain primitive F primeth root of unity. And you can see whatever F prime was, it's that root of unity is already contained in your K, in your L. So this extension L tilde is the same as L. Okay. Now this T is a group of order 3, cyclic. Therefore, okay, and it's contained in L star. So it has only 3 characters, namely the trivial character, which I denote by 1, and it's of degree 1. Degree is not the right word. Order is the right word. It's a character of finite order, and that order, the trivial character is of order 1, of course. Then there's this theta. Theta is just the inclusion of T in L star. And the order of this character is, of course, 3, because T is of order 3, right? So, and once you have theta, you also have theta squared, which is also of order 3. So this group T has only 3 characters because it is of order 3. And I've given them names. They are the trivial character, which is denoted by 1, this one, and not this one. This one is a number. This one is a character. Okay? And so I'm calling them 1, theta, and theta squared. Now you have this group sigma, which acts on the set of these 3 characters, right? By raising, so it acts on L tilde, and therefore it acts on the group of characters, right? Sigma is the Galois group of L over K. So it acts on L tilde, and therefore it acts on all maps to L tilde, and it's not L tilde, L star. And therefore it acts on the group of characters from T to L star. Fine. And what are the orbits for this action? Because it's the orbits that we were interested in. That was the first component of the pairs that we were looking at. We were looking at pairs, where the first component is an orbit. So it's clear that, of course, the trivial, there's the orbit containing the trivial character, and it contains no other character. Then theta and theta squared are in the same orbit. Why are they in the same orbit? Because right. So this T is so this theta bar consists of theta and theta squared. That's because this L, yeah, L exactly. L is a degree 2 extension of K, and the Galois conjugation is given by raising to the power 2, right? So theta and theta squared are conjugate under the action of sigma, right? Okay, so they give you this orbit theta bar, and of course the size of this orbit is 2. Okay, so now these lambdas, remember we were looking at pairs consisting of chi bar, comma, lambda. So we have determined these possible chi bars. We have determined the possible chi's. They are 1, theta, theta squared. And then we have determined the possible chi bars. They are 1 bar and theta bar. They are just 2 orbits. And now we have to see what are the possible thetas, lambdas, excuse me. And of course, that what the value, the possibilities for lambda will depend upon the orbit that you are looking at. For this orbit, there might be more possibilities. For some other orbit, there might not be that many possibilities. But actually, if you look at the definition of lambda, then you will see that in both cases, lambda equals 1 is the only possibility. So you get how many representations? You get just 2 representations of this G. G is S3. You get the representation corresponding to the pair 1 bar, comma 1. 1 bar is this orbit 1 bar, and this 1 is the lambda equal to 1, right? And the other representation that you get is rho theta bar, comma 1. Theta bar is this orbit consisting of theta and theta squared, and 1 is, of course, this lambda, which is equal to 1. And this one, this representation is of degree 2 because the orbit has size 2. So these are representations of this S3 defined over L. These are the only, they are absolutely irreducible representations. And normally they are defined over L tilde, but here L tilde is equal to L. So you get these 2 representations of this S3 defined over your L. Now we were interested in F2 representations. Remember P is equal to 2, and we are looking at FP representations. So when P is 2, we are looking at F2 representations. L is a finite extension of F2, and we know the representations over L, there are 2 of them, this one and this one. What do they give? Do they give rise to, how many representations do they give rise to over F2? That's the question. So they'll give rise to as many representations as there are phi orbits. Phi is the Galois group of, normally it's perhaps L tilde over F2. But L tilde is equal to FL, so it's the Galois group of L over F2, right? And you can check that, in fact, the action of phi is sort of trivial in the sense that there are 2 orbits, namely the orbit of 1 bar, comma 1, and the orbit of theta bar, comma 1. So you get 2 representations. So the first one is, of course, going to be the trivial representation because, and the second one is a representation of degree 2, because the degree over F2 is the sum of the degrees over L tilde, and the sum is taken over all representations in the same orbit. But because there's just one representation in this orbit, you will, which is of degree 2, you'll get degree 2 representation over F2. Okay, so if you just call it the second one, the degree 2 representation, if you just call it pi, then you see that pi, viewed as a map from G to GL2 of F2, is actually an isomorphism. So once you have this kind of a map, I mean, this kind of a map is, of course, a linear action of G on F22, this vector space F22. But this vector space is, of course, also a group. So you can take the semi-direct product of F22 with respect to this action pi with G. So that can be seen to be isomorphic to the group S4. That's isomorphic to the group S4. G itself is isomorphic to S3, and this F22 semi-direct product with G is isomorphic to S4. So that's the other example which one should keep in mind, because we might come up, we might have to come across this again, right?
Sir, this degree of irreducible F2 representation also depend on sigma element, sigma orbit. Am I right?
That's right. But the sigma orbits here consist of one element each. So there's no orbit which has more than one element. In other words, the action of sigma is trivial. Sigma just, yeah. That's right. So that's something which is not very difficult to check. And so let's now go on to so I'll skip these two sections 25 and 26, and we will come to this part about irreducible representations, FP representations over P fields. So what does that mean over P fields? It means that when the group that you're trying to represent is the absolute Galois group of a P field, right? So those are, of course, infinite fields, infinite groups, profinite groups. And we have been discussing representations of finite groups. How is that going to help? So we'll see that this is actually this theory that we have been discussing is exactly what's needed in this case to fully classify these FP representations of the absolute Galois groups of P fields. Okay. So now I have to fix the notation. So let K be a P field. P is a fixed prime number, and capital K is a P field, and little k is its residue field. Earlier also I had a little k, and that was a finite extension of FP. So of course this k is also a finite extension of FP because k is a P field, right? And Q is the number of elements in K as before. Now the new thing is V naught, V and K tilde, these three things. They are all extensions of K. So let me begin with K tilde. K tilde is the separable algebraic closure of K. It's equal to the algebraic closure in characteristic 0, but it's different from the algebraic closure in characteristic P. It's smaller. It's because it's required to be separable. And the algebraic closure of FP power series T is not separable over FP power series T. FP power series T has some inseparable extensions, like inseparable algebraic extensions, like you adjoin a pth root of T. That is an inseparable extension of FP power series T. That extension, FP power series pth root of T, that extension, which is inseparable, is of course not contained in K tilde. K tilde contains all finite separable extensions of K. But inside this K tilde, you have the maximal unramified extension, which is V naught. And you have a further extension containing V naught, which is the maximal tamely ramified extension of K in K tilde. So the picture is as follows. You have K at the bottom, which is contained in V tilde, not V tilde, V naught, which is the maximal algebra. I mean, it's the, what is it called? The maximal unramified extension of K. V naught is the maximal unramified extension of K. It's Galois over K, and the Galois group is Z hat. Remember, Z hat is the product of ZP for all P's. ZP is for a specific prime P. You have Z2, Z3, etc. But if you take the product of all these rings, Z2, Z3, etc. for all P, then you get Z hat. And the additive group of that Z hat is the Galois group of V naught over K. Then you have V, which is the definition is that it is the maximal tamely ramified extension of K in K tilde. So it contains all finite tamely ramified extensions of K in K tilde. In particular, it contains V naught, which is the okay. So you have these three things. Now you put gamma naught equal to the Galois group of V naught over K. It's isomorphic to Z hat, but I mean not just isomorphic, but there's also a canonical generator, namely the Frobenius element. What is the Frobenius here? It's the Okay, so the way to explain it is that this gamma naught is, or let me put it this way. So this V naught also, of course, comes with a discrete valuation because it's an algebraic extension of K, which has a discrete valuation. And when the residue field of V naught is an algebraic closure of this K, which is the residue field of capital K. So there is the Galois group of the residue field of K, V naught over K. That is, of course, isomorphic to Z hat. When I take any finite field, take the algebraic closure, which is the same as the separable algebraic closure, and I take the Galois group, I get Z hat with a canonical generator. And that generator is raising to the power Q, where Q is the number of elements in the finite field I started with. So in this case, when I look at the Galois group of V naught over capital K, I have a map to the Galois group of the residue field of V naught over little k, which is the residue field of capital K. And that map, that reduction map, is an isomorphism. So gamma naught is, by this reduction map, is isomorphic to z hat. Okay. Then you have this gamma, which is the Galois group of V over K. And of course, gamma naught is a quotient of this gamma. And the kernel is, something which can be described, because we have described all tamely ramified extensions, right? So basically, it's the product of, it's isomorphic to the product of all ZPs. ZPs is not a good way of saying it, because P is fixed. So it's a product of all ZLs, where L is a prime. L runs through all primes, except the prime P. Hello?
Yes, sir.
You can hear me?
Yes, sir. Yes, sir.
Okay, good. I thought something happened. Fine. So, yeah. Now, here is an important remark, that the FP representations that we are interested in are the representations of this Galois group of K tilde over K. But so the important remark is that they all factor through gamma. And why do they factor through gamma? Now, this is due to the fact that, of course, this gamma is a quotient of this Galois group, right? This gamma is a quotient of this Galois group, right? Because you have, let me see if I can use the pen and draw this sort of diagram of fields. You have K here. No, I think it's not really possible. Anyway, so gamma is a quotient of this absolute Galois group, because this V is contained in K tilde. Fine. But why do irreducible FP representations of this group factor through gamma? That's because of the following circumstance. First of all, the kernel of the map from this Galois group to gamma is a pro-P group. Is the wild inertia. This is what we have seen, right? The ramification filtration on the Galois group of an extension of local fields. You have the whole group, you have the inertia subgroup, then you have the wild inertia subgroup. And that wild inertia is always a P group or a pro-P group. That's one thing. And the other thing is that if you have a P group acting on an FP space, then you never get an irreducible representation. There's always some invariant subspace. So because of this circumstance, every irreducible representation of gamma of this Galois group will factor through gamma. So what I'm saying is nothing, I mean, it's not about local fields or anything. It's a purely algebraic fact. Let me say it again. Suppose I have a group G, and I have a normal subgroup P, capital P, and the quotient is G mod P is called gamma. Now, the hypothesis is that this capital P, which is a subgroup of G, is a little p group, meaning it's a group of p power order where p is a prime number. And I'm looking at irreducible representations of gamma over the finite field Fp. The claim is that then every such irreducible representation of G will factor through its quotient gamma. Okay, so that was the thing which must have been explained in the introduction, and so now we are basically interested in the irreducible representations of gamma. That's one. Okay. So you have some more notation before we can actually come down to it. So for every n, you have En, which is p to the n minus 1, and then an extension Vn of V naught, which is obtained by adjoining an En root, Enth root of pi, where pi is a uniformizer of k. Of course, this pi, which is a uniformizer of k, is also a uniformizer of V naught, right? V naught, the valuation of V naught is also discrete. So one can talk about uniformizers. And why is it discrete? Because V naught is unramified over k. But which uniformizer do you choose in order to attach its Enth root? The point is, it doesn't matter which pi you choose. Because if you choose a different pi, you'll get the same Vn. You'll get, and why is that? Because it contains this V naught contains the Enth roots of every unit. Oh, let me, yeah, there's a simpler reason than this, because suppose this pi is a uniformizer of k. If you choose some other uniformizer, it will differ from this pi by a unit of k. And this unit of k, you can always extract Enth root of that unit, but En is, of course, visibly prime to p. So when you extract an Enth root of that unit, you'll get an unramified extension of k, and that extension is contained in V naught, because V naught is the maximal unramified extension. So that's one thing. The other thing is that this V naught, of course, also contains an Enth root of unity. When you join an Enth root of unity, also you'll get an ununified extension. So it's contained in V naught. So V naught contains a primitive p to the n minus 1th root of unity. And therefore, this extension really is independent of the choice of pi. Okay. Now this Vn is also not only Galois over V naught, but it's also Galois over k. Right? Because you can think of it as adjoining the Enth roots of everything in k. Actually, it would have been simpler to write, you adjoin the Enth roots of everything in V naught. Yes, that's what, adjoining the family Enth roots of everything in V naught star. Yeah, exactly. So this Vn is Galois over k, and you are calling gamma n the Galois group of Vn over k. So this Vn, of course, is a quotient of gamma. This gamma n is a quotient of gamma because Vn is contained in V. It contains V naught, but it's contained in this V because V is the maximal tamely ramified extension, and you are getting tamely ramified extensions here, right? Okay, and this V is actually just the union of all these Vn's. And therefore, this gamma is the inverse limit of all these gamma n's. So these gamma n's are some special quotients of gamma. And right. But if the only thing to note is that if P is equal to 2, then V1 is equal to V0. So V1 is obtained by E nth roots, and n is equal to 1 and P is equal to 2. So 2 minus 1 is E1 when P is equal to 2 is equal to 1. So you are joining 1th roots, which means that you're not joining anything. And therefore this V1 is equal to V0. That's only when P is equal to 2. Otherwise, I mean, this V1 is different from V0. Okay. So we also note that, this if the characteristic of K is 0, then, I mean, these Vn stars have elements of order P, because V1 contains this element here, and therefore it contains a primitive pth root of unity. This we have seen, right? Adjoining to QP, primitive pth root of unity is the same as adjoining a P minus 1th root of minus P, right? This we have used several times. Okay, so that's the notation. Another way of explaining what Vn is to say that it's the compositum of all finite extensions of K of ramification index dividing En. En, remember, is here, p to the n minus 1. And that's it. So that's, if you don't remember what was done here, you just think of Vn as the compositum of all finite extensions of K of ramification index. So tamely ramified extensions automatically, because the ramification index divides En. You fix N and you look at all extensions whose residual degree is allowed to be arbitrary, but the ramification index divides this En, and take the compositum, and what you get is Vn. Okay. Now, the first observation is here that if you are looking at irreducible FP representations of gamma, I mean, here we had said that we are only interested in the representations of gamma now, because initially we were interested in representations of the Galois group of K tilde over K, which is the absolute Galois group of K. But we have seen that they all factor through gamma, and therefore we are only interested in irreducible representations of gamma. Now, we are saying that if an irreducible FP representation of gamma, the degree of such a representation divides N, then it factors through this quotient gamma N of gamma. And this gamma N is a specific quotient. It's a small quotient. It's far from being so. In some sense, where is it? Here, did it say? Yeah. This V is the limit of all these Vn's. And if we are saying Vn's are small, but it's a sort of increasing family, and V is the union of all these things. And we are saying that if the degree of an irreducible representation of gamma divides N, then that representation factors through the quotient gamma N of gamma. So that's very interesting, because the gamma N is much more concrete, and it's a much smaller group, so we can write down the representations more explicitly. Okay, so here's a proof, and I mean, you can just look at it. It's not Yeah, it's not very long. Okay. So now we might ask, see, so here, this is the question that I'm discussing now. This question here, it says that, this group gamma, first of all, it is generated by just two elements. I told you that its quotient gamma, what is it called? Was it called gamma naught? No, it was not called. Did it have a name? This gamma naught has not been defined, but yeah, but like the group gamma is actually generated by just two elements, and there's just one relation between them. This we must have discussed when we talked about tamely ramified extensions and which of them are Galois and what is the Galois group in that case. So roughly speaking, you have forget about this notation. Let's consider a P field K and a finite extension L of K. The hypothesis is that it's a tamely ramified Galois extension. Then there's a Galois group, the Galois group of L over K, and there's an inertia subgroup. So if G is the Galois group, then G naught is the inertia group. And then there's the quotient, G modulo G naught. The quotient is the Galois group of L naught over K, where L naught is the maximal unramified extension of K in L. So this quotient G modulo G naught, it comes with a canonical generator. Let's call it little sigma, and sigma to the power F is equal to 1, because if F is the degree of L naught over K. And the kernel of this quotient map is the inertia subgroup G naught. Now we know that the inertia subgroup comes with a map theta naught. Anyway, it's cyclic of order E, where E is the ramification index, right? E is the degree of L over L naught. And doesn't have a special generator. And the action of G modulo G naught, let's call it sigma. The action of sigma on G naught coming from this short exact sequence is raising to the power Q, where Q is the number of elements in the residue field of the P field K. So this Galois group G has a presentation consisting of two elements, sigma and tau, and the conjugation action of sigma on tau is given by sigma tau. Sigma inverse is equal to tau to the power Q. So that is what the presentation of the Galois group of a tamely ramified extension of P fields looks like. I mean, there's a presentation like this. Why am I discussing this? I'm discussing it because I want to say that, yeah, is there a question? Somebody asked a question?
Oh. No, sir. No, sir.
No. Okay. So I want to say that there are only finitely many FP representations of this gamma of given degree n. Why are they only finitely many? Because a representation is determined by a homomorphism from a group is determined by its values on a system of generators. And this gamma has a system of generators consisting of two elements. And so each of those generators can be sent to some elements of the target group, but the target group here is a finite group, GLN FP. Of course, the target elements have to satisfy the same relation as these two generators. But I mean, that only further cuts down the number. So if I count the number of maps from the set of those two generators to this group GL and FP, there are only finitely many maps, right? And therefore, there are only finitely many maps satisfying some additional relations, and therefore there are only finitely many representations. So if there are only finitely many representations, then there's a finite extension M of K such that every irreducible FP representation of gamma of degree dividing n factors through this M of Galois group of M over K.
Sir?
Yes.
Sir, can we say that if we can relate the irreducible representation by the equivalence classes of the group G? So by that way, we can say that this has finitely many irreducible FP representation.
Yeah.
Because, we can say now.
Yeah.
We can relate.
We are not in characteristic 0 here, but yeah, that might also work. If you can parameterize them by conjugacy classes, then of course there are going to be finitely many conjugacy classes, and you can get finiteness that way as well.
Okay, sir.
Right. Okay. So the question is, since there are only finitely many representations of a given degree n, there has to be a finite extension M of K such that all these representations factor through this Galois group of M over K. And when n is equal to 1, we have seen that they all factor through this. This is what we had. So when n is equal to 1, we are looking at characters with values in FP star, right? And we have seen that all characters factor through this extension, this Kumar extension, right? So what happens if n is greater than 1? That's what we are going to discuss now. Okay. Okay, so here it is. So if n is greater than 1, then you define Kn to be obtained from K by adjoining an Enth root of unity. That's an ununified extension of K, right? Because you are joining an Enth root of unity, and En is prime to P. K is a P field, and En is prime to P. So when you join an Enth root of unity, you get an unramified extension. And what is the degree of that extension? That is just the order of Q bar in this group, right? That's a standard thing. And now you put Ln to Kn, you adjoin the Enth roots of everything in Kn star. That's a kind of maximal abelian extension of Kn of exponent dividing En. So that's also a tame linear unified extension, and therefore it's contained in Vn. And actually Vn is just Ln compositum with V0. Okay. Now, so So the next statement says, number 33, says that every irreducible FP representation of gamma of degree dividing n factors through this finite quotient Gn, let me call it, which is the Galois group of Ln over K. This is a finite quotient of gamma because this Ln is contained in the field V. Now that's very interesting because this group, the group Gn, is a very specific concrete group, right? We have, because it is a quotient, the Galois group of Kn over K. So it's a cyclic group of order Sn, and Sn is the order of Q bar in this, right? And the kernel of this map, of this quotient map, is just the Galois group of Ln over Kn, right? And that is easy because that's Kn modulo K star, Kn to the, what is it? Yeah. So it's going to be Kn star modulo Kn star to the power En. So it's a very concrete kind of a thing. Okay. So this statement is proved here. It's a slightly involved proof, but I encourage you to read it. I mean, it's not very long. The principle must be, I think it must be straightforward, so I'm going to skip it. And so let me summarize what we have done. We have a P field K, capital K. We are interested in the absolute, I mean not absolute, irreducible FP representations of the absolute Galois group of K. Why are we interested in these things? Because we had parametrized primitive extensions of K of degree P to the N with certain pairs consisting of a degree N irreducible representation of the absolute Galois group, and then the second term was something else. But so the first component was an irreducible representation of that absolute Galois group. So we are now in these two lectures, we looked at the irreducible representations of the absolute Galois group of this P field K. And what have we achieved? What we have achieved is that all these irreducible representations are factored through this this group Gn, and Gn is a finite group. It's a very not only is it a finite group, it is the kind of group that we had discussed in the previous lecture. So we know how to write down all irreducible FP representations of a group like this. And therefore, we know how to write down all reducible representations, FP representations of gamma. And therefore, we know how to write down, which are the same as all irreducible FP representations of the absolute Galois group of K, the Galois group of K tilde over K. So the first part, the lecture on Monday, the previous lecture, was totally abstract in the sense that we were not looking at any specific fields. We were just looking at group theory and representation theory. So this explains why we were looking at that particular kind of groups. because in the case which interests us, the Galois group of the absolute Galois group of a local field, or this group gamma, the irreducible FP representations of such groups of gamma, they factor through this quotient Gn, which is a group of the kind that we had discussed last time. Okay, so let's look at those three examples. We had examples of the cyclic groups and an S3 example. And so the final thing that we can do today is to look at these examples. But before that, are there any questions? Okay, if there are no questions, let's look at this case where P is equal to 2, right? P is 2, N is 2, and E2. What is E2? E2 or En is P to the N minus 1. And P is 2 and N is 2, so E2 is 2 squared minus 1, so it's 3. Then this Q, what is Q? Q is a power of 2, right? It could be congruent to 1 modulo 3, or it can be congruent to minus 1 modulo 3. Now you can check that if it's congruent to 1 modulo 3, this K2 is actually equal to K. And L2, this notation is what we have been discussing. No? K2 is obtained from K by adjoining, excuse me, a primitive E-nth root of unity. So, but it already contains a primitive, K already contains a primitive E-nth root of unity. En is, we should not talk about En, E2. E2 is 3. So, you see, why is K2 equal to K? We had, where is, yeah, Kn is here in number 32. So it's obtained by adjoining an E-nth root of unity to K. So in our case, it's going to be adjoining a third root of unity. But Q is congruent to 1 modulo 3. So Q minus 1 is divisible by 3, right? And therefore, this capital K contains a third root of unity. That's right. That's so K2 is equal to K. Right? You get it? Because, okay, yeah. So K2 is equal to K, and L2 is obtained from K2 by adjoining the E2th roots of everything in K2 star. So it's this here. So it contains the n-ramified cubic extension and the 3 ramified cubic extensions, and all of them are cyclic over K, right? So that gives you back these examples that we had discussed, or it's before this. Yeah, yes, these examples in number 23, the Z mod 3 example and the A3 example. The difference between these two is that Z mod 3 is the quotient in the sense that it is a canonical generator. Here F is 3 and E is 1. Whereas in the A3 example, F is 1 and E is 3. Okay. And but if this q is equal to -1, I don't know how I managed to get that. Anyway, so if q is equal to -1, then k2 is no longer equal to k, right? That k2 was equal to k when q was congruent to 1 modulo 3. But if k is congruent to -1 modulo 3, then k2 is actually a quadratic extension of k, right? So you need to adjoin cube root of 1. And so you get a quadratic extension. And this L2 is the ununified cubic extension So this L2, of course, it remains the definition of L2 remains the same. Here, same as this, except that now you have to write K2 instead of K, because K is no longer equal to K2. So this L2 contains the ununified cubic extension and the unique S3 extension, namely this one, of K. So we get the S3 example of number 24 that we start with today. So this is all I have to say. So let me summarize what we have been doing and why we are doing it. Our aim is to parameterize, just as we have parameterized degree p extensions of p fields, we want to parameterize degree p to the n primitive extensions of p fields, right? Degree p extensions, we had parameterized them in terms of, so we had this auxiliary field. We had the base field k. From k to k, you adjoin the p minus 1th roots of everything in k star. So you get some finite extension of k of degree p minus 1 squared. It's a Galois extension. And then the Galois group adds on, let's give this extension a name, right? E. Or does it, maybe here it already has a name? Yeah, it has this, I think the correct name for it would be L1, right? Is it? Yeah, because this, we are calling it Ln here. Did I say somewhere that L1 is really the same as this K star modulo K star? No, not modulo. K star adjoint. Yeah, here. It's called L1. Right. So let me repeat. We have prime number P, we have P field K, and we want to understand or parameterize the set of all degree P extensions of K. So cyclic, no, not cyclic, separable. Cyclic would have been easier, we did it earlier, but we now want to, then we did this separable case. So for that, you just look at this L1. L1 is obtained from K by adjoining the P minus 1th roots of everything in K star. It's a Galois extension of K, and if G is the Galois group, then G acts on L1 star modulo L1 star to the power P, and it's the G stable lines which correspond to the set of, which correspond to separable degree P extensions of K. G stable lines in L1 star modulo L1 star to the power P. So we want to do something similar for primitive extensions. Now, primitive extensions of degree P to the N. So for that, we have this field Ln. This L1 can be thought of as obtained from K in two stages. You first obtain K1, which is just K here in this case, and then you obtain L1. So the generalization is that you have this Kn, which is obtained by joining an Enth root of unity to K. And En, remember, is p to the n minus 1. En is e to the n, or it's not e to the n, e sub n is just p to the n minus 1. So you first take your Kn, and then because it contains a primitive Enth root of unity, I can talk about Kumar extensions, and Ln is the maximal abelian extension of Kn of exponent dividing En. So Ln is going to be Galois over K, and the Galois group of Ln over K will act on not just Ln, but on Ln star and on Ln star modulo Ln star to the power P, just as in the case Ln equal to 1. Okay, and now it's going to be so let's call Gn the Galois group of Ln over K, right? So Gn acts on Ln star modulo Ln star to the power P. And the primitive extensions of degree P to the n of K are in bijection with irreducible sub-representations of this representation of Gn of degree n. So that's why we have tried to, we have determined all irreducible degree P representations, and I've just given you an idea of where they are going to be needed. So they're going to be needed in order to, ultimately, in order to parameterize the set of primitive extensions of K of degree P to the n. Okay, so as I told you, this paper is available on the archive, and it's also something which I've put on Google Drive devoted to this course. So you should be able to access it and take a look at it and read it. Send me an email if you have any questions, and yeah. So that's it. So next week we are going to take up a new topic, which is so we have looked at irreducible representations here. So the new topic is going to be, yes, as I said, there is this the group Gn. Where is Gn? Yeah, this group Gn here. It'll act on Ln star modulo Ln star to the power P. So, and this Ln is a terminally ramified extension of K. So we are going to study this kind of, we are going to determine very explicitly the action of this Galois group on Ln star modulo Ln star to the power P, not just in this special case, but for any terminally ramified extension. So this is the case we need, but the general case, which is of any terminally ramified extension, is not any more difficult. it's perhaps even easier in the sense that it frees you from the peculiarities of this particular case. So what we are going to do is next time is to take a finite tamely ramified Galois extension of a P field. Let's call the extension L and let's call the P field K. And let's call G the Galois group of L over K. Then this group G will act on L star modulo L star to the power P. And we are going to determine the structure of this as a module under the group G. That's a very interesting thing. In a sense, we have done a special case of this. What is the special case that we have already done? So that special case is when that group G is actually this Gn here. G1, excuse me, not Gn, G1. We have studied this action or this module structure when we proved Serre's mass formula. So in that case, we had to look at G stable lines, G1 stable lines, and so we had to study this. And actually, we had to sort of be careful about the character through which G1 acts on that line, whether it's the cyclotomic character or some other character, because that made a difference as to what the that made a difference as to the exponent that we were looking at, right? So we will have to do something similar, and in fact more precise in the case of Gn. And as I said, not just Gn, but any tamely ramified Galois extension. Maybe we need the hypothesis that it should be a split extension. So what is split in this context? We have a tamely ramified extension. So you have the Galois group, you have the inertia subgroup, and you have the quotient. So you have a short exact sequence. Now, that short exact sequence doesn't always split. But it can be, by enlarging the extension a little bit, you can always make it split. So if it is split, then many of the things are simpler, and therefore we will look only, in any case, our GNs are going to be split. So we are going to look at the split case only. So that's going to be next week. And maybe I'll stop here today, unless you have some questions. Are there any questions?
No, sir.
Okay.
We will study this paper.
Right. So see you on Monday then. Before that, there's a tutorial on Friday. Okay then.